Fischer esterification is vital to organic chemistry because the ester product is one of the most important functional groups in drug design. It involves the reaction of an alcohol with a carboxylic acid. The alcohol functional group consists of an OH bond. The oxygen atom in this bond acts as the nucleophilic species as it is electron-rich and has 3 lone pairs of electrons that are shared with other molecules called electrophiles to form new covalent bonds. In the carboxylic structure, the delta-positive carbon acts as the electrophile because it is electron-poor and accepts the electrons from the oxygen nucleophile. However, the OH bond is too weak and the carboxylic acid's delta-positive carbon isn't positive enough to allow this reaction to proceed. Therefore, a very strong acid catalyst such as sulfuric acid is required to increase the other molecules' reactivity. A Fischer esterification occurs in a series of steps including protonation, attack of the nucleophile, intramolecular proton transfer and elimination. When sulfuric acid is present, the sp2 oxygen on the carboxylic acid attacks the acid, taking one of its hydrogens and breaking the bond holding that atom to the molecule. The electrons from this bond go to the most electronegative atom, which in this case is the oxygen. This forms the sulfate anion as a result. This process is known as protonation, as a proton is added to the carboxylic acid. The next step is the attack of the nucleophile, which can proceed since the delta-positive carbon is now positive enough to allow the alcohol to attack. The alcohol forms a new bond with the carboxylic acid branching from the delta-positive carbon. However, carbon only ever forms 4 bonds, so the oxygen from the carboxylic acid steals the electrons held in the double bond, reducing it to a single bond. This now obeys the octet rule. However, an intramolecular proton transfer must now occur as you cannot have an acidic and a basic group on the same molecule. The basic oxygen takes the hydrogen from the alcohol, which stabilizes the positive charge as the oxygen takes the electrons from the bond. With the addition of a hydrogen, a molecule of water is now attached, which is a great leaving group. In the elimination step, the sulfate anion steals a hydrogen from the OH bond on the carboxylic acid. It does this as it wants to return to its original form as sulfuric acid. The electrons from this bond are used to reform the double bond to the oxygen atom. The leaving group also leaves during this step. The final products of Fischer esterification are the sulfuric acid catalyst and the ester.
Created using Powtoon.